Okay. So what is electrochemistry? Um, Chemistry is all about the movement of electrons, really. You know, protons are deep within the nucleus, so protons can't really move around or do anything. However, the electrons are not bound super tightly to the atoms. So the protons are bound very strongly to the nucleus because of the strong force. The strong force holds them together. So there's a huge amount of energy holding them together. But the electrons are not held as tightly. So the electrons can move around. And the movement of electrons is really what causes chemical reactions. Um, so if you study organic chemistry in the future in college or something like that, you'll see that the movement of electrons are represented by arrows. So organic chemistry is all about depicting the movement of electrons in reactions. Okay. So sometimes we can harness this movement of electrons to create electricity, so electric current. So this is the principle behind batteries. So there are many different kinds of batteries, but fundamentally all batteries use chemical reactions. So for example, in some batteries we have a reaction between manganese dioxide and zinc, for example. Another common example would be the lead acid battery in your car. So the lead acid battery is a reaction between lead 4 oxide, so PbO2, and lead metal, and they react to form lead sulfate. And this creates a movement of electrons, which is used to create a very high voltage to turn on the spark plugs and create electricity in your car. So your computer or your phone also probably has a lithium ion battery. So I have here a schematic of a lithium ion battery. So in a lithium ion battery, we have on one side, the anode, we have graphite, so carbon, and the lithium ions, which are represented by red, go in between the layers of graphite. So they intercalate, but then we have this kind of polymer separation, and the lithium ions can move through here. And in here, we have this lithium metal oxide. So this is a compound of lithium, oxygen, and some metal. So I've seen cobalt being used. So lithium cobalt oxide. And this movement of lithium ions is what creates the electric current that powers your phone. So the advantage of lithium ion batteries is that you have like these lithium ions, there's a lot of energy being stored in a small amount of space. So this is just one example of the use for electrochemistry batteries. Okay, so today in this lecture, what we want to do is understand how these reactions work and calculate some voltages based on that. So, for example, how do we calculate the voltage of a battery? So, here are some examples of electrochemical reactions in industry. So, so one major electrochemical reaction is bleach production, so making chlorine gas. So, chlorine gas is made by passing electricity through a solution of sodium chloride. So take some table salt, add it to water, and pass a current through it, and you'll generate chlorine gas on one wire. On the other wire, you generate what's called sodium hydroxide. So Li. So here we have Li, sodium hydroxide. This is very corrosive base, and the idea is that if you pass the chlorine gas through a solution of sodium hydroxide, you'll create a mixture of sodium hypochlorite and sodium chloride. This is called a disproportionation reaction. So I can draw it here. Where's the annotate there? So the reaction is something like this. Yeah, something like that, and then plus H plus or something. Um, so we have chlorine going to chloride and hypochlorite, and then this mixture of chloride and hypochlorite is what's inside of bleach. So bleach is equal parts sodium chloride and sodium hypochlorite. Additionally, aluminum metal is made by electrochemistry. So most metals are usually made by, you take the metal oxide. So for example, iron oxide. So some examples are Fe2O3 and Fe3O4. So these metal oxides, these compounds of oxygen and the metal you want, and you react it with something like carbon. So for example, you heat it at very high temperatures with carbon, or you can use another metal like magnesium. So that's how we make most metals. But aluminum oxide, so Al2O3, aluminum oxide is very stable. So it turns out that these methods won't work. You cannot break apart aluminum oxide just by using carbon and heat. So in industry, what they do is they take this vat of molten aluminum oxide. So you have this huge vat of molten aluminum oxide mixed with cryolite. So cryolite, Na3 AlF6, cryolite, and that lowers the melting temperature. I believe they also use calcium oxide to that, calcium oxide. So you have this mixture, and it's molten, and they pass huge amounts of current through here, through the mixture, which generates the aluminum metal, and the aluminum metal is molten, so it can be drained off. So interestingly enough, a large portion of the world's aluminum is made in Iceland, even though Iceland doesn't have any aluminum ore. So there's no aluminum in the Icelandic soil or anything. It's just that Iceland has this huge reserves of geothermal energy. So electricity in Iceland is very cheap. So they make aluminum in Iceland. So they ship the aluminum ore to Iceland, then they make the aluminum in Iceland, and then they ship the aluminum out. So kind of strange, but okay. So we're going to introduce you guys to redox. So this is the heart of electrochemistry. So here we have two reactions. Sodium plus chlorine goes to sodium chloride, and hydrogen plus oxygen goes to H2O. So in the first case, remember that sodium chloride is made of these ions. We have Na plus and Cl minus ions, right? So that means that the sodium is losing an electron to form Na plus, and chlorine is gaining an electron to form Cl minus. In other words, the sodium is transferring an electron to chlorine. So we have this transfer of electron density. So at first, the sodium has some electrons, but now the chlorine has the electrons. So the chlorine has gained some electron density, and the sodium has lost some electron density. So we have this transfer of electrons and electron density. So this is what constitutes this is what causes a redox reaction, some change in electron density. So, however, in the second case, our hydrogen reacting to oxygen, we form a water molecule. And remember, a water molecule has covalent bonds. So electrons are actually being shared in that case. So the transfer of electron density isn't really super obvious. But what you have to notice is that in the water molecule, we have oxygen, which is a very electronegative element, and we have hydrogen, a much less electronegative element. So the oxygen atom really has most of the electrons in the water molecule. So we can consider electron density moving from the hydrogen molecule to an oxygen atom. So again, we have this transfer of electron density. Okay. So, okay. So in that above reaction, we can consider that to be the sodium plus chlorine goes to sodium chloride. it really has two parts. So so in the first step, we take a sodium atom and it loses an electron to form sodium plus. So it loses an electron, and we call this oxidation. Okay, so we call the loss of electrons oxidation. And in a battery or an electrochemical cell, this would happen at the anode. So oxidation will happen at the anode. Conversely, our chlorine is gaining electrons. So a gain of electrons is called reduction. And the reason why it's called reduction is because you're reducing the charge. So at first, it's chlorine with a charge of 0, but then it becomes chlorine with a charge of -1, and -1 is less than 0. So we're reducing the charge. So this gaining of electrons is called reduction, and it happens at the cathode. So, and we'll discuss the structure of electrochemical cells later to clarify what anode and cathode mean. And what's important to remember is that reduction is always accompanied by oxidation. So there is no chemical reaction that will actually produce electrons because electrons are very, very reactive, right? Electrons are very, very reactive. So free electrons don't really exist outside of very strange circumstances. So if we have one reaction where we're losing electrons, some other reaction has to gain the electrons because we can't just have free electrons. So reduction and oxidation always happen together. So if something is getting reduced, something else has to get oxidized. So here are some two mnemonics. So oil rig, oxidation is loss, reduction is gain of electrons. And red cat, so reduction happens at the cathode. Oh, there's another one I know. So oxidation and anode both begin with vowels, and reduction and cathode both begin with consonants. So that's how I used to remember it. So here the sodium is getting oxidized. So it's the reducing agent or the reductant, and the chlorine gas is the oxidizing agent or the oxidant. So the oxidizing agent gets reduced and the reducing agent gets oxidized. I'll give you a minute to write that down. So, let's see. Let's do an example, I think. I think an example is good. Okay. So let's look at the reaction. How about this? Okay, wait, it should be. AlCl3. So how about this? Which one is the oxidizing agent? Which one is the reducing agent? And write the two half reactions. Okay, so I'll give you a minute to do this. Up aluminum chloride. What ions are in this substance? Cl3 plus and Cl minus. So therefore, we have two reactions. Right? So which one of these is oxidation and which one is reduction? Remember, oxidation is a loss of electrons, and reduction is a gain of electrons. So here, the aluminum is losing 3 electrons to form Al3 plus. So aluminum is being oxidized. However, aluminum is also the reducing agent because remember the reducing agent gets oxidized. So you can think of it this way. The reducing agent is the thing that's helping to reduce the other chemical, and the oxidizing agent is helping to oxidize the other chemical. So here we have reduction. We're reducing Cl minus to Cl2 to Cl minus. Okay. Should we do one more example? So how about this? So can you complete this reaction? So complete this reaction. I'll just tell you actually. Mg 3 and 2, and then 2, write the half reactions. So let's just do this one. So should go here and here. So we need to balance the reaction. So what numbers go there? Let me turn off the light. We have one of these, so we need 3 magnesiums, and we have only 1 and 2. So which ions are in here? What 2 ions do we have? So we have what? Yeah, and Mg2 plus and nitrogen 3 minus. So can you tell me what the oxidation half reaction is? It's very fun. So we have 3 magnesiums go to 3 Mg2 plus. However, since we have this 3 here, you need to multiply 3 by 2, so we have 6 electrons. And what about the reduction half reaction? Great. So we have nitrogen gas. However, we need to multiply the 3 by 2 because we have 2 nitrogens. So each nitrogen is gaining 3 electrons, and we have 2 of them. So it should be plus 6e minus. Oops. Okay. And what I want you to notice is that we can cancel some stuff out. So this cancels out, and when we add them together, we got the same as before. Notice this is the same as here. Okay? So I think we can move on now. Okay, so What are some examples of redox reactions? So if you've taken a biology class, you might recognize this picture. So here we have basically what happens inside of the mitochondria. So what happens inside of the mitochondria? And the mitochondria a lot of these are redox reactions. So here we have oxygen getting reduced to water, and we have NADH getting oxidized to NAD+. This is not a redox reaction. Here we have oxygen getting reduced to water, and of course the citric acid cycle. So what's going on here? So let me try to remember back to AP Bio. So what happens is that glucose will get oxidized into acetyl-CoA. So glucose eventually gets oxidized to acetyl-CoA. It first goes through pyruvate, though. So glucose gets oxidized to pyruvate, and pyruvate gets turned into acetyl-CoA. But remember that oxidation is always accompanied by reduction. So when glucose gets oxidized to pyruvate, it reduces NAD+ back to NADH. So here we can see the reaction. NAD+ plus 2 electrons goes to NADH, and here's the reaction. So this is called glycolysis. So glycolysis produces NADH, and it oxidizes glucose to acetyl-CoA. Then acetyl-CoA will make its way through the mitochondria. It makes its way into the mitochondrial matrix, where it enters the citric acid cycle. So you can see here's the citric acid cycle. And in the citric acid cycle, another redox reaction happens. If I remember correctly, the citric acid cycle will eventually, the citric acid cycle will consume a molecule of acetyl-CoA, and it spits out molecules of CO2. So we're oxidizing acetyl-CoA into CO2. And then you breathe out the CO2. But remember, this oxidation reaction has to be accompanied by a reduction. So we reduce even more NAD+ to NADH, and we reduce some FAD+ to FADH2, if I remember correctly. So now we have all of this NAD+ and FADH too. So now your body has this buildup of NADH, and how do we get rid of it? So NADH gets oxidized back into NAD+, right? So NADH loses electrons to form NAD+. But then this oxidation reaction has to be accompanied by a reduction reaction. So alongside this, oxygen, which is a very strong oxidizing agent, gets oxidized to water. Gets reduced to water. So oxygen is an oxidizing agent, so it gets reduced to water. And this reaction is very favorable. So the reduction of oxygen is really what drives this whole thing. And when this reaction happens, it actually produces these H+ ions. So you can see this reaction produces H+ ions, which enter the outer membrane. So the space, the intermembrane space, the space in between the inner and outer membranes, actually becomes rather acidic. So now we have this different in pH. So inside the mitochondrial matrix, we have a low pH, and outside the mitochondrial matrix, we have inside the mitochondrial matrix, we have a high pH, and outside the mitochondrial matrix, we have a low pH. So this means we have a difference in H+ concentrations. So the H+ will diffuse across, will kind of want to go into the mitochondrial matrix. And this is really one of the more amazing pieces of biology. The movement of these H+ ions drives a molecular machine called ATP synthase. And let me see if I can draw a schematic of that. So you can see, imagine we have imagine we have this membrane, and then ATP synthase kind of looks like this. So we have two parts. So I guess you can look this up later. I can't really draw this super accurately. But basically, we have this component here. And this component spins. And this component spins 1,000 times per second. Okay? So inside your body, you have these molecular machines that are spinning at thousands of times per second. So as fast as a jet engine. And they're all getting pushed by the movement of H+ ions. So the H+ ions move into here, move in this direction, pushing the rotor of ATP synthase 1,000 times per second. And this rotation converts ADP, this rotation drives parts of the ATP synthase protein that converts ADP and phosphate into ATP. So all the time inside your body, you have these amazing molecular machines that are moving incredibly fast, and they're all driven by redox reactions. So these are all redox reactions. So this is just some redox reactions in the body. But of course, there's some other ones. So battery discharging. So when a battery discharges, we get the movement of electrons, and these electrons flow through circuits. So in the computer, they flow through the circuits in like the motherboard and the CPU and the hard drive, which makes the computer run. And bleaching is also a redox reaction. So, for example, if you ever gotten like carrot stains or something like that, or like carrots or like stains like that. So basically, we have this structure, which is a long chain of carbon atoms, and you have these alternating double bonds. And these alternating double bonds are what cause the color to appear, because it means that the electrons are kind of delocalized throughout the entire molecule, and these electrons are easily excited to other energy levels. And this excitation absorbs light energy, which creates the color. So the goal of bleaching is not really to remove the dye itself, but we want to destroy the dye. We want to convert the dye to a form that cannot absorb this light energy. So the relevant reaction here is we have these double bonds, and they react with hypochlorite, the hypochlorite ion. And the reaction is something like this. So what's the end product? You have what's called an epoxide plus a chloride ion. And notice how the double bonds aren't connected anymore. So that means that they aren't what we would call conjugated anymore. So this disrupts the absorption of light, and you don't see any color anymore. So this is basically the principle of how bleaches work. And what's interesting is that the bleach doesn't actually remove the dye. Like the dye molecule, the stain is still there. It's just that it converts it to a form that you don't really see. Okay? So the goal isn't to remove the stain, it's just to make it not visible. Okay. So, so far we've only really done problems with very, very simple redox reactions with ions. However, remember, so hypochlorite is not an ion, but it still goes redox reactions. The dyes aren't ions, but they still do redox reactions. They aren't simple monoatomic ions. And especially in the biological example, the molecules are very, very complicated. They're not these simple monoatomic ions, but we still need to be able to like justify these redox reactions. So what we use is oxidation state. So oxidation state allows us to, oxidation state is really more of a formalism. It's a way for us to keep track of electrons, but it's still useful. So the basic idea behind oxidation state is we take the chemical bonds between atoms and we assign the electrons from the bonding pair to the more electronegative element. Let me see if I can show you. So let's say we have a molecule of formaldehyde. So formaldehyde preservative. So here's the structure. And what we can do is we can write it as more of a dot structure. So I'll try to do that. So you can see these 4 electrons will form the bond. So we have our 2 bonds here. And now what we do is we give the electrons in those bonds to the more electronegative element. So can you tell me, so what's the most electronegative element in formaldehyde? So your options are C, H, and O. So rank them from most to least electronegative. So great. So oxygen is the most electronegative. So that means that let's consider this bond first. So these 4 electrons will go to the more electronegative element. So now we have this. And then, oh, sorry, that shouldn't be there. And then we have this. So how many valence electrons do we have there? We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons, 8 valence electrons. How many valence electrons does a neutral oxygen atom have? Great, 6. So 8 is 2 more than 6. So we have 2 extra electrons. So that means that we can say the oxidation state is O2 minus, because we have this 2 minus comes from the 2 extra electrons. Now, the carbon gets, so carbon is more electronegative than hydrogen. So the electrons in these bonds go to carbon. So in the end, we get something that looks like this. Now, what's the oxidation state of this carbon atom? Difference. So what should the oxidation state be? Great, 0. So you have carbon 0. And what about the hydrogens? Can you just do the hydrogens? What is the oxidation state of the hydrogen atom? So, great. So the hydrogen atom doesn't actually have any electrons, because the electrons in the bond all go to carbon. We don't give hydrogen any electrons. So what should it be? Great, 1 plus. So this is the basic idea behind oxidation state. So there are some other minor rules. So let's say we have 2 atoms, 2 of the same element connected. So we have 2 identical elements connected. Then we split the electrons equally. Okay? Now here's a way to check your work. You add up all of the oxidation numbers, and then the sum of the oxidation numbers must equal the total charge of the molecule or ion. Okay? So in our previous example, we had 2 hydrogens, each one was 1 plus. We had a carbon that was 0, and we had an oxygen that was -2. So 1 plus 1 plus negative 2 is 0. And the overall molecule also has a charge of 0. So we've done it right. Great. And here are some other tips just to make your life easier. So any pure element has an oxidation state of 0. So O2, Cl2, and 2, P4 all have oxidation state 0. They're all pure elements. Any monoatomic ion, any ion that consists of only one atom, has oxidation state equal to its charge. So Cl minus, O2 minus, they have a -1 oxidation state and a -2 oxidation state, respectively. And when we form compounds, things are a bit more tricky, but what you can remember is that the 1A metals, so lithium, sodium, and the lithium, sodium, etc., are all going to be +1, almost always. The 2A metals, so beryllium, magnesium, calcium, strontium, and barium, they will almost always be +2. Hydrogen is usually +1, with the exception of the metal hydrides, so compounds of metals and hydrogen, which you will probably never see. And oxygen is usually 2-. The major exception is hydrogen peroxide. And fluorine is always going to be -1, except for the pure element. So in compounds, fluorine is always -1. I don't believe there are any exceptions, because fluorine is the most electronegative element, so we always give it the electrons. So let's do a slightly trickier example. So how about this? Oops. So can you tell me what the oxidation states are here? So what are the oxidation states? What's the oxidation state of hydrogen? So how about this? Let's just split it up first. So let's change all of the bonds to pairs of electrons. So each bond has 2 electrons. So what's more electronegative, oxygen or hydrogen? Oxygen, right? So so we're going to give all of the electrons here to oxygen. And likewise here. Now, oxygen is the same electronegativity as oxygen, right? They're the same element, so we split the bond equally, right? And then, of course, we already divided it up here. Now, with these divisions in place, can you tell me what the oxidation states are? Okay, well, yeah, so this is 1-, right? Because we have 1, 2, 3, 4, 5, 6, 7 electrons instead of 6. So it's 1-, and of course it's the same. So now we have to balance out this 1-, so this should be 1+, right? And notice you could have just derived this using our other rule, because hydrogen is almost always 1+. So, and we need to, so that just makes all the other oxygens 1-. Okay? Should we do, I guess we can do one more slight trickier example. So can you determine the oxidation states here? And I'll throw in an Na+. So sodium nitrite, what are the oxidation states? Okay, so can you check again? Make sure you counted right. So what's more electronegative, oxygen or nitrogen? Oxygen, right? So all of these electrons go to oxygen. So that means the nitrogen doesn't have any electrons, right? So if it doesn't have any electrons, what's its oxidation state? Well, normally in nitrogen, how many electrons does a normal nitrogen atom have? A neutral one. 5. So now we have 0. So it should be 5 plus, right? And the oxygens are each 2 minus. And what's the sodium? What about the sodium atom? 1 plus. And notice we have to multiply this by 3. So 5 plus 1 plus 3 times minus 2 equals 0. This is also 0. So it's good. Let's see. How about let's take a 10-minute break. So come back at 8:03. So now we're going to actually look at some redox reactions. Okay. So let's say we're given a random redox reaction and we need to balance it. So there's a few steps that we can always follow. So the first step is to determine the oxidation states. And then we can create, using these oxidation states, we can create 2 half reactions. Once we've created the half reactions, all we need to do is balance the electrons in each of the half reactions. And then, and that's all you need to do for some simple redox reactions. So, for example, here we have a very simple reaction between cerium-4 and tin-2. So common reaction, pretty common electrochemistry reaction. So here we have some cerium-4 plus. So cerium ammonium nitrate has a very nice orange color. And yeah. So let's see. What's the reaction? We have plus. So what are the oxidation states here? So we have 4 plus and then 3 plus. So one of the half reactions is this. Is going to be C4 plus E minus goes to 3 plus. And contrary, and likewise, we have SN2 plus goes to SN4 plus 2E minus. Now we need to combine these in a way that the electrons all cancel out. So what should be the final reaction? What should be the balanced reaction? In other words, what should we do to combine these reactions so that the electrons cancel out? Electrons, and here we gain 1 electron. So we need to multiply this by 2 so that we're gaining 2 electrons, we're losing 2 electrons, and overall the electrons are balanced. So now what we have is Ce4 plus, 2Ce4 plus 2E minus goes to 2Ce3 plus. And then all we do is add them together, and here's the end result. Okay? Okay. Use a different sheet of paper. And is it bleeding so much? Okay. Unfortunately, not all redox reactions are that simple. So a lot of reactions involve other atoms like oxygen and stuff that we need to deal with. So, and it turns out that a lot of these redox reactions are an aqueous solution. In other words, dissolved in water. So it kind of depends whether the water is acidic or basic. So for a more complex reaction, we do the above. If it's an acid, we balance the charge in the reaction using H+, and if it's in base, we use OH- to balance the charge. And then all we need to do is add H2O molecules to either side to balance out everything. So let's do this example. Here we have permanganate reacting with formic acid. So, interestingly enough, formic acid is named formic acid because it comes from ants. Goes to CO2 plus manganese 2 plus. And this reaction occurs in acid, which I've specified in the problem. So, now we have to identify the oxidation states. So what do you think the oxidation state here should be? What's the oxidation state of manganese? Each oxygen is going to be 2 minus. Usually oxygen is 2 minus. So if each oxygen is 2 minus and the overall charge is 1 minus, what should manganese be? Present it this way. The charge on the oxidation state of manganese is X plus 4 oxygens, and each one is 2 minus. So negative 2. And this needs to equal the total charge, which is minus 1. So what's X? Now, can you do the same thing here? So remember, oxygen is minus 2, H is plus 1. So what's the oxidation state of carbon? Can you check your math? X plus, so we have 2 hydrogens, and each one of them is plus 1. And then we have 2 oxygens, each one is minus 2. And then the overall charge is 0. So what's X? Right, plus 2. And what's the oxidation state for manganese 2 plus and CO2? Plus 2. What's the oxidation state? Simple monoatomic ion, right? And for the simple monoatomic ions, the oxidation state is simply the charge on the atom. So what should it be in this case? Right, 2 plus. And what's the oxidation state for carbon here? How do you get 0? So remember, assume that each oxygen is 2 minus. If you assume that each oxygen is 2 minus, what do you get? X plus 2 oxygens and each oxygen is 2 minus, and this equals 0 because the overall charge is 0. So what's X? Right, 4 plus. So now we can create these two half reactions, and they aren't going to be balanced, but that doesn't matter. And what should I put in the blank? I've left a blank here. What should I put there? How many electrons go there? How many electrons go here? Right, 5 electrons. And here we have what goes in this blank? 2 electrons, great. Okay, so now we have two half reactions. So what should I do to make the electrons cancel out? So I need to multiply this by some letter, let's just say R for reduction. And here we have some letter O for oxidation. So we need to multiply these reactions by some number to make them cancel out. So what should we do? What should we do? Right, R equals 2, O equals 5. So when we add these together, we get this. We're almost there. Now we need to balance out charge. So what's the total charge on this side of the equation is 2 times 2 plus, right? So it should be, we write 4 plus here. And the total charge here is 2 minus. We need these charges to be the same. And we do this by adding H plus because we're an acid. If it were in base, we would add OH minus, but this is an acid. So what should I do to make the charges cancel out? I need to add H plus ions. So close. So we do need to, okay. So this side is more negative. So we need to make this side equal 4 plus. We need to somehow make this 4 plus. So what should we do to make the left side equal 4 plus? Right, so we need to add 6H plus. And we're almost there. The only problem is that the oxygens are not balanced. Here we have 8 plus 10, so we have 18 oxygens. Here we only have 10. So what should I do to balance out the oxygens? $18 oxygens. And here we have only 10 oxygens. Yeah, so we need to add H2O, and we should add 8 H2O to this side, right? Because we need more oxygens here. So the final reaction is this. Oh, 8. So that's the final reaction. So this one is a bit tricky, actually, but if you practice this a lot, it should get easier. Additionally, I just want to make a note. So this is why if you ever do a reaction like this in your AP chemistry class or something like that, like some kind of redox reaction, you will need to add acid to the reaction because you can see the reaction consumes a lot of acid. Okay. Yeah, so adding more acid helps the reaction go faster, which is usually a good thing. What's next? Okay, so I'll give you 15 minutes to balance these reactions, I guess. So they go from easy to hard roughly. So this one's pretty easy, this one's a little harder, and this one's fairly hard. But so I think 15, we'll just do 15 minutes, okay? Yeah, that's correct. What about the second one? Can you tell me what the two half reactions are? What are the two half reactions? So yeah, what are the two half reactions? We have Li plus, oh, sorry, Li goes to Li plus, and then we have H2O. Now, what numbers should I put here? What should I put there? So 1 E minus. What about here? So this hydrogen is +1, and this one is 0. Well, there's two hydrogens, so yeah, 2. And then so we multiply this reaction by 2. And then what should I put here? Oh, here, 2. What should go here? This is in base, so we add OH minus. So we need 2 OH minuses to balance out the 2 Li pluses. And now we have 1 oxygen here and 2 oxygens there. So we need to add another H2O and everything's balanced. So this is the answer. Okay, and did you try the last one? So what about the last one? Oh, I made a mistake. So I actually made a mistake, but can you tell me what you got regardless? That's fine. I'll go over it. I actually made a mistake. It should be Cr2072 minus, not Cr207, which does not exist. But we'll just do this. Notice we have 2 chromiums here, so we need to put 2 chromiums there. So the first reaction is pretty obvious. It's just Fe2 plus goes to Fe3 plus E minus, right? The second one is probably a bit difficult though. So what's the oxidation state of chromium here? we have, let's just call the oxidation state X. We have 2 chromiums, so 2X, and we have 7 oxygens, and then each one of them is going to be 2 minus equals -2, because the total charge is 2 minus. So what's X? Right. So we have this. And we're going from +6 to +3. So what should I put in the blank? So, well, we have, so each chromium is going from +6 to +3. So each chromium gains 3 electrons. And we have 2 chromium atoms. So, should be, so look closely, we have 2 chromium atoms. So it should be 6 E minus, because each chromium atom is gaining 3 electrons. And then we have 2 chromium atoms, so we have 6 E minus. And then of course we have, so then we have, this needs to be multiplied by 6. So we have, and this is an acid. So what should we add? What should we do? Well, what's the total charge on this side? So we have 6 times 3 and 2 times 3. Let me make sure that's right. 18 plus, so 18, it's 24, right? So 24. And what about on this side? Great, 10 plus. Now we need to balance the charges. So what should we do? What should we do? Remember, we're an acid, so. So we need to add 14 because the difference between 10 and 24 is 14, right? And additionally, we need to add them to the left side, right? Because this side is more positive than this side. So we need to add more positive stuff to this side. So we add 14H plus. And then we just need to add 7H2O to balance that out. Okay? So this is the final reaction. And just some interesting fact about dichromate. So this ion is called the dichromate ion. And we have this equilibrium. If I remember correctly. And notice when we add acid, the reaction goes in this direction. So this is why I chose to do the reaction in acid, because the dichromate ion exists in acid. When we add base, the equilibrium goes in this direction, so we form chromate. So this is why I did it in acid. And interestingly enough, the dichromate ion is a very nice orange color, and the chromate ion is very nice yellow color. So it turns out back in like a long time ago, maybe like the 60s or something, they used to paint buses they used to paint school buses with lead chromate. Lead chromate because lead chromate has a very, very bright yellow color. It's a school bus yellow. So they used to paint school buses with lead paint, and then they realized lead is not good for you. Lead is an example of a heavy metal. It messes with your brain. So they stopped doing that. Okay. So for a while, they were painting school buses with lead. So that's where school bus yellow comes from. Okay. So I have a nice picture here. So you can see we have a copper wire, and we've put it in a solution of silver nitrate. So we have silver ions in the beaker. I actually have a picture. I actually have a thing of this. I did this a long time ago. I don't know how you can, if we go to the camera, you see I have this file here, and there's a copper wire in there, and there's some zinc, there's some silver powder, and here's another one. So that's that reaction. And you might note, you might notice that it goes from colorless to blue, and that's because copper 2 plus, the copper 2 plus ion is blue. So what you see that this copper wire gets covered in these beautiful silver crystals over time, and the solution turns from colorless to blue. And this experiment is also sometimes known as Diana's tree. So Diana, the goddess of the moon, because silver is associated with the moon. Okay, interesting. So, okay, how much time do we have? Okay, we don't have too much time left, so I just wanted to give you an overall idea of this. We probably won't do too many calculations. So imagine we have some high energy electrons. We have the uphill electrons, and then they go to a lower energy place. So the electrons are going from high energy to low energy. So they will flow. The analogy is a ball rolling downhill. But instead of a ball rolling downhill, we have electrons moving through a circuit and through the light bulb to generate some light. I have such a setup here. So when I connect the terminals, when I connect, why would I go? When I connect the terminals, the electrons are flowing through this wire, and then they go into this bulb, which I believe is an LED. So the electrons flow through the bulb, and then that generates light. So on one side of the battery here, we have the electrons come out of one side, and they come out of the side where the oxidation reaction is happening, right? Because the at the oxidation part of the reaction, you're losing electrons, so the electrons come out, and then reduction, we're gaining electrons, so the electrons flow in. So So in a battery, we also have two half reactions. So, and this movement of electrons, we can call it an electrical action, which is driven by an EMF, an electromagnetic force, electromotive force. And this electromotive force is measured in volts. So you might have heard of like a 1.5 volt battery, or the really heavy duty 6 volt batteries, or those little 9 volt batteries. Wall power is off of 120 volts, if I remember correctly, and in Europe it's 220. And this reaction has E naught equals, so this voltage And it's not, so this is at standard state, so everything is going to be 1 molar. We have E naught equals 1.1 volts. And volts means joules per coulomb, by the way. A coulomb is a measurement of electric charge. And what I want you to notice, this is really handy, is that if we multiply the reaction by 2, the voltage doesn't change, because voltage is measured in joules per coulomb, not joules per like mole or anything like that. Because it's in joules per coulomb, it doesn't care about how many times we've multiplied the reaction. So that reaction also is 1.1 volts. Okay? But of course, the reverse reaction, this reaction has a negative sign. So if we go in this direction, we have that reaction will be negative 1.1 volts. And so a reaction with a positive voltage will be favorable because we have a positive EMF. If we have a negative voltage, the reaction is unfavorable. And of course, you can measure this voltage using a voltmeter. Okay, so I'm just going to briefly mention standard potentials. So suppose we want to find the voltage for a half reaction, because when we create reactions, all we need to do is add the half reactions. So if we can have a table of half reactions, we can very easily find the voltage. The problem is that all half reactions have to be accompanied by another half reaction for them to occur. So it turns out it's very, very difficult to measure the EMF, the voltage of a half reaction. However, what we do is we can compare the voltage of the reduction half reaction to the reduction of H plus. So 2H plus goes to H2. And this is called the standard hydrogen electrode. And the setup is this. So we have a platinum wire connected to a piece of platinum foil, which increases the surface area. It's powdery platinum, increases the surface area, makes the reaction go faster. And this is immersed in an inverted tube of hydrogen. And this hydrogen is going to be at 1 bar or 1 atmosphere. A bar is about the same as an atmosphere. And this whole setup is immersed in sulfuric acid, actually usually hydrochloric acid, with a concentration of 1 molar. So H plus equals 1 mole per liter. And the temperature, of course, is at 298 Kelvin. And we hook this electrode up to our the electrode we want to study. We can measure the voltage, and we can tabulate all of these values to get what we call standard reduction potentials. And what I want you to notice is that the more powerful oxidants have more powerful reduction potentials, have more positive reduction potentials. We don't have much time left, so I suppose I can just, so here's a diagram of an electrochemical cell. So this is basically, this is kind of what a battery looks like. This is a lot less compact than a battery, of course, but it's the same idea. So here we have H plus, so here we have 1 electrode, and I believe, so in this case, this is the cathode, because we're reducing H plus to hydrogen gas. So here we have the cathode, and you can see that electrons flow towards the cathode. Here we have a strip of zinc metal, and the zinc loses its electrons to form Zn2+. And because we're at standard state, the concentration of zinc is maintained at 1 molar. So we have this, so here we have the anode because we're oxidizing zinc to zinc 2+. So the electrons are flowing over here. And the problem with this is that we have all of these electrons flowing over here. So we should expect this portion to become negatively charged. But this is impossible because everything has to remain neutral. So we have to counteract this negative charge. And to do that, we have what's called a salt bridge. So here we have a piece of maybe paper or some kind of gel, and and this gel is soaked, or a semi-permeable membrane, and or a piece of like cloth or something like that, and it's soaked in a solution of some salt. Usually, I've seen like potassium nitrate or something like that. So this is completely, so we have a bunch of ions in here, and the positively charged ions can actually move in here to counteract the negative charge that's flowing in. Okay? So this is kind of a diagram of a battery. And I think it's 9 o'clock, so I think we have to end the lesson now. So we didn't get to cover the Nernst equation or this kind of stuff, but I'll send you a web page that if you want, you can read about it. Okay? So, yep, that's the end of today's class. So I'll see you guys later.